Thank you again, everybody, for joining us for today's webinar, Power on Demand, Renewable Energy Storage. My name is Colleen Elliott. I'm the Manager of Education and Special Events here in the Office of Alumni Relations. We acknowledge that the University of Alberta is located on Treaty 6 territory and respect the histories, languages, and cultures of First Nations, Métis, Inuit, and all First Peoples of Canada, whose presence continues to enrich our vibrant community. Dr. Martini's presentation today is approximately 35 minutes in length. We'll be taking questions throughout the presentation, which you can submit in the Q&A box, and he will answer some of them at the end of the presentation. Again, you can type it at any time in that Q&A box. It should appear on your screen, likely at the bottom and sometimes up at the top. We'll have approximately 20 minutes afterwards for Q&A. In a moment, you'll see Dr. Martini and his presentation slides. If you find that the on-screen photo of Dr. Martini is covering part of the presentation, you can move it by simply clicking on it and dragging it to a corner so that it's off of the slide. The University of Alberta Alumni Association is a supportive, proud, global network of graduates collectively making extraordinary contributions to the alumni community, the university, and the public good. Part of our mission is to connect, engage, and support alumni by providing lifelong learning opportunities for personal and professional growth. Thank you to Dr. Martini for helping us with this mission today. Dr. Pierre Martini received his PhD in mechanical engineering from the U of A. He is now a principal investigator in the U of A's Future Energy Systems Research Program. Pierre works in both conventional and renewable energy sectors. His research and development work includes industrial collaborations and consulting, primarily in composite materials and structures for conventional and renewable energy sector applications. A dedicated teacher of solid mechanics and engineering design, Dr. Martini is the recipient of several teaching awards, including the Summit Award for Excellence in Education by APEGA. Welcome, Pierre Martini.
Okay, hello everybody. Just gonna share my screen. So everybody should be able to see my screen right now, I hope. And let's get started. So today I would like to talk to you a little bit about power on demand and energy storage. And this talk has been given before in various forms at alumni events and also for future energy systems. Let me just see. Here we go. Now my slide changed. So Colleen already did a great job introducing myself and pointing out what I do. I would like to kind of make a couple extra comments. One is I did my graduate degree at the University of Alberta, but my initial engineering education happened actually in Germany. So if I sound funny, if I have an accent, my apologies. That's my German heritage. And also, I have like a fairly global perspective when it comes to energy systems. So, you know, being from Germany, which is arguably one of the leaders in renewable energy implementation in their energy sector, I've been following that fairly closely. And so I have this perspective, but I'm also living in Alberta for like 20 years now. So I understand the Alberta situation also quite well. Also, I'm not making any, policy, and I'm not politically biased. I'm really trying to be an engineer, scientist, and go by numbers. And so the presentation today will be talking about that. I still have some problems here switching slides. Why is that? Here we go. So I would like to start with this slide. So this I found in a newspaper like a few weeks ago, like it was published actually in October 2019. So Mr. Warren Buffett, arguably, or as we know, one of the very influential and very financially powerful people of this planet, he announced that through one of his companies, they will invest $200 million in southeastern Alberta So that's the Medicine Hat and Lethbridge area, I assume, to create wind farms there. And so that's not insignificant investment, and the wind farm is also not insignificantly small. So it's quite a large wind farm. And I assume that Mr. Buffett does this not for, to make this the world a better place. He probably does this for financial reasons. So the question is, why does wind get his attention, and why does his company invest in this technology? So this got a little bit. This was kind of like one of the motivations for this presentation, because as I said, I work in the area of energy storage, but it actually starts with the topic of renewable energies, and I will talk a little bit about the different the points that you see in front of you right now. There are renewable energy that I would like to talk about. Opportunities and challenges. I will talk about energy storage, a little bit of what's possible and what's realistic. And thank you for a number of you who already sent in questions in the last couple of days asking about things. And I unfortunately will not be able to answer all of the questions about energy storage. It's a pretty broad field. But my goal is to just point out the highlights, and I'm happy to have later discussions with you if you're interested. After this event is over, you can get in touch with me by email. I will show you my email address at the end of the presentation. And then I would like to kind of finish my talk by going into the very specific work that we're doing in my smaller research group, which is part of the Future Energy Systems initiative here at the University of Alberta. And that's energy storage using flywheels. So another article that was in the newspaper was this particular one, also showing the interest that companies have in green energy. And so apparently this creates some excitement, as it says here, in the Alberta renewable energy sector, because we do actually have some excellent conditions to create energy from wind and solar. So here we see wind turbines. I was actually lucky enough to see them this winter. The wind turbine farms, they're in the southeastern Alberta, and it's quite impressive when you see the installations. If you ever been to Europe and you drive through places like Germany, I mean, there are like wind turbines pretty much everywhere, right? So question is, why this interest in wind and solar? And I picked out this diagram here that is from a reputable agency, and it shows the global levelized cost of electricity from renewable energy, and these are all utility scale type of sources. And so you see in this graph, the different versions of renewable energy, so biomass, geothermal, hydropower, solar, and then the wind turbines like offshore and onshore. You can forget about the offshore here in Alberta, so let's look only at onshore. And then I hope you can see that. I mean, at the bottom, there's a comparison always between 2010 and 2017 for each of those different renewable energy sources, and a cost range. So, so many dollars per kilowatt hour of energy. And there's a darker band here that stretches across the whole diagram. That is kind of the fossil fuel range. So gas, oil, coal. So those fall into in this band, and it depends a little bit. I mean, Alberta, be very aware of the oil price all the time, possibly even the gas price. Sometimes it's very high, sometimes it's very low, but that's typically where their conventional energy carriers kind of play out. And we can see now that in the 7 years that this diagram kind of specifies here, or I guess 8 years, that onshore wind is actually at the lower end of the band of conventional energy carriers. Hydro has always been very cheap, but again, has not been a big player in Alberta. And then even solars, photovoltaic, which was a few years ago, like 2010, significantly expensive. Now it's like also competitive with the conventional energy carrier. So that's pretty much the reason why, at least I think, people go into renewable energies, because it's cost effective and it's cheap. And as a consumer, I don't want to pay a lot for my power that I consume at home. So I think just basically without any political bias, there is a good reason why people invest in renewable energies. But not everything is great about renewable energies. And this is a German expression, and I'm not sure if anybody is actually or speaks German here in the audience. So I think there will be a poll in a moment. What does kalte Dunkelflaute, that's the word, actually mean? And it's a technical term. So engineers use this in Germany. So and then if you speak German, we can kind of string words together to make whatever long winded word. So this is one of those. It's an artificial word. Like 20 years ago, this word did not exist, but it does today. And let's see how many people know what this word means. Here we go. Here are the results. Cold, dark, lull. Correct. So 43% of you got it right. Let's see if I can close this poll here. Yes. So kalte Dunkelflaute means cold, dark, lull. So a time when it's cold and dark without any wind. And that's a nightmare for energy providers. As you probably all know, the electricity grid is a very fine balance between supply and demand at the current stage. So whatever is consumed has to be provided. So we cannot, that grid cannot really store any electricity. The power must be provided on demand. And that causes problems if you have a lot of suppliers in there that are intermittent. So we know that the sun doesn't shine at night, so solar wouldn't be providing any electricity at night. And wind is very depending on the weather, right? So if it's a non-windy day, that's a problem. And especially in jurisdiction like Alberta, it's a little bit of a challenge because we're not very well connected. As you know, in Europe, Germany sits in an excellent place, with France being to the a close neighbor, which has a lot of nuclear power. There's mountainous regions around, like Austria and even Norway today, that has a lot of hydropower that can store electricity and sell it back to the Germans. So in Germany is also to create changing their energy infrastructure to try to compensate for this cold, dark lull. And it's quite stunning when you see how much the mix of energy generation changes in Germany right now. So the maximum ratio of, or the percentage of energy supplied from renewables, so wind and solar, the record currently in Germany lies by 75%. So on a normal average day, that is more like 27%, which is still great, 27%. But on the day when the wind was blowing all over Germany and the sun was shining and 75% that creates a problem for the electricity grid, right? At the same time, if there's no sun and no wind, and suddenly you're losing 27% of your electricity, that's not good either. So there's some issues. Another issue, that's something I had to learn from my colleagues who are economists, is the way power markets are being regulated. So it's a competitive system, and I created this little diagram. Actually, I have to say, I kind of modified it. My colleague, Tim Weiss, who's also part of the Future Energy Systems initiative, he created that diagram originally. So this is the way our power grid is being regulated, and it's called the merit order effect. So let me explain this graph a little bit to make sure you understand where I'm coming from. So we have on the vertical axis here the power price, which is in dollars per megawatt hour. It actually goes up to $1,000. That's kind of what we do actually in Alberta here. And at the bottom, we have the power that could be supplied to the grid. And so it says here, the gray curve is the so-called power pool bids. So everybody could be you, if you have a wind turbine in your backyard and you want to sell your electricity that you generate to the grid, you would be bidding in this system. So you put your bids in, and so all these different units, like let it be coal-fired power plants, gas-fired power plants, wind turbines, solar panels, whatever, all bids for in this pool, and then at the bottom line, this gray curve keeps increasing along the horizontal axis. And initially, interestingly enough, everybody puts a 0 bid in. So initially, everybody just kind of puts a 0 bid and just be part of the club, essentially be able to provide power. Then when it becomes like the power demand becomes pretty high, some premium suppliers start bidding, so at a higher cost. And then it shoots up to the very end here, which is the real premium. And this peak here at $1,000, it turns out that we actually reached this in this winter. I think it was in January. There was one day where it was dark and it was cold and there was no wind and a very high power demand in Alberta. And we were at $999. So we almost maxed out on this policy. So now we have a certain sample demand at one day. So like all the people and all the businesses in Alberta use a certain amount of power. And that's just this red arrow, this vertical arrow, points out to some kind of power that's being consumed from the grid. And wherever this demand line crosses the bidding line, that is the price that's being set for all the bidders here to the left. So all units that have been bidding to the left of the red arrow get this particular price. So at this point, for this example here, it's around between $45, $50, which is kind of typical kind of thing. So let's say that's on a windy day. That's how everybody's kind of doing their thing. Wind is blowing, turbines are rotating, all the other power plants are active. And we can see now, let's identify the little different bidders here a little bit. So the ones that go in first typically are wind and solar. They have no marginal cost. There's nobody working there really. They have no fuel cost. So the only thing is the capital cost. You have to build those and a little bit of maintenance, but really they just bid always. They always go into the mix right away because in the bidding for 0, in the hope that they get the demand is high enough so they get some money out of it. Cogeneration, that's the folks that are creating heat and electricity at the same time. So they have no choice because they're providing heat to cities, they're providing heat to large organizations like the University of Alberta. So they have to generate electricity and heat at the same time, also have no choice. Then large power plants like coal-fired power plants in Germany would be also like nuclear power plants. They're also bidding typically at 0 because these power plants can be hardly regulated. So they are designed to put out a certain amount of power, and it's hard to turn the knob to change the amount of power that they can provide. So they're also going in and running pretty much at a steady state and kind of bidding at 0. But then there are the premium suppliers. So in Alberta, increasingly we get more and more gas-fired power plants, a combined cycle. It means they're using gas turbines to burn gas, train turbines, create electricity, and then use the exhaust heat from the turbines to boil water, create steam, and run steam turbines. They're very effective power plants. So we're getting increasingly more of these in Alberta. Hydro, we don't have a lot in Alberta, but this is, again, you could use hydropower. Like this would be pumped hydro. We get to this a little bit later. And then peak bids. So these are the folks that are going in and say, we can turn something on that would otherwise not be running. And we'll get to this later. You can probably already imagine what peak bids are. This could be energy storage devices. And actually hydro is an energy storage system. So bottom line, intermittent and unvarying power providers, they have no choice. They're bidding at 0. And the dispatchable ones, they're bidding at the higher dollar values typically. They wait until the price is high enough. So what happens now if we get to a day when the wind doesn't blow? The same is true if the sun doesn't shine. So then this gray curve, which is kind of bluish here now, this blue curve, becomes the red curve. So the low wind curve is like the wind, remember in the previous slide, the wind suppliers were part of the bidding pool. They're always in there, but they're dropping out. So the curve simply shifts over. But demand, typically doesn't change, right? So people still need to run their businesses. They still need electricity. So demand changes, it doesn't change. So now the red curve is the actual curve that we're looking at, and the demand line crosses, the red curve at this point at a higher dollar value. So now all the power suppliers to the left get this new price, which is now above 100. And again, when we had this situation in January, they all got close to $1,000 per megawatt hour. So But the losers in this, when it comes to the high price regime, are actually always the renewables. So renewable energy, as soon as that wind doesn't blow, you know, all the conventional energy carriers, the gas-fired power plants, and so are the big winners, whereas the renewable energies are the big losers. And if the wind blows a lot and we have a lot of solar and wind installed, then there's more zero bidders in there. And again, they make very low dollars at this moment because the high price bidders, they don't even kind of go in there. So anyway, it's not an ideal situation for wind. So if we could store the electricity that's being created by solar or it's generated by solar and wind and use it for later and then be one of the peak bidders, that would be ideal. And let's look a little bit of energy storage devices. Again, there's another poll popping up here. So if you can, want to answer this question, what is the most common energy storage technology? I didn't specify that anymore. It could be like globally, not so much in Alberta, think globally. So let's start talking a little bit. The one that we are most familiar with is probably batteries, right? So everybody, knows batteries like, the dry cell batteries that you use like to run like your, I don't know, a toy or a flashlight or so, right? So these are belong to this group, but also more advanced like lithium-ion batteries that you find in the electric car and those kinds of things, right? So batteries are, and as soon as the poll is done, my team here, you can just kind of pull in the pumped hydro. Yeah, that's correct. We get to this in a second. This is the most common technology. So more than half of you are right. So batteries are great for mobile application, especially like in your cars and your flashlight, things that need to be carried or taken around. But for stationary applications, they're not so great. Also it's a chemical reaction in the battery. So there's, often some chemistry involved that is difficult for creating the battery, running the battery, and then also recycling the battery later on. So there's some environmental impacts with batteries that may not be easily resolved if this is a large scale issue. Pumped hydropower is, as you said correctly, it's by far the most common storage technology. Here the idea is that you have two reservoirs of water. Typically that's done in a mountainous area where you have large like valleys available. So you're pumping water from a lower level to a higher level when electricity is cheap. And so times when solar is good, when wind is good, you use electricity to pump water to the higher part and then into a higher reservoir at a higher elevation. And then later on, when the power price, when you want to be, the wind doesn't blow, or the sun doesn't shine, and the power price goes up, then you actually let the water run down through a turbine into the lower reservoir again, and you create electricity and you sell it for a good profit. So this is very common in mountainous areas. Unfortunately, Alberta is not very mountainous. In the mountainous areas that we have, to the west, lots of us are national parks, and it's difficult to find the space because they're very intensive on the land use. So you need a lot of space. They're very, you can imagine you flood a valley with water. It's like very disruptive to the wildlife and the people who live there. So this is Alberta is not ideal for pumped hydro. BC is a different story, but even there, areas where you can do this are limited because again, you need a lot of space. Thermal storage is an interesting one, not very common. Here you melt some kind of solid, like a salt, with electricity. You heat it up, it stays liquid for a while, and then you can cool it down again and create steam or something in the process and run a turbine. That's an interesting technology that is emerging. Supercapacitors, again, good for a short burst of power, but not really for, you hear the word sometimes, it's not really a technology for like grid scale electricity storage. Let's see the next, pneumatic storage. I got a question actually from somebody sent to you, from this week sent to you. Yeah, it's something that is emerging, coming up. So you pump, when you have electricity available for cheap, you pump gas like air underground into caverns deep underground, pressurize the gas there, and then later on you let the gas come back out again and let the gas expand and through a turbine and create electricity that way. It's not the most efficient way of doing things, but in some areas it may make sense if you pump essentially just a benign gas like air underground. The one I want to talk to you today are flywheels. That's really my field of research. And so I will talk to you about what a flywheel is and how it works and why I think it's an interesting technology. A flywheel is an electromechanical battery, it's so to say. So whereas the electrochemical batteries that I mentioned earlier uses chemistry, a flywheel is a system that uses mechanical motion to store energy. So advantages of a flywheel is they're really good in being charged very quickly and discharged very quickly. So I have my cell phone here lying beside me. Oh, can't see it. So if you have your cell phone, it takes a while to charge it. And it cannot be charged super quick. It can be charged like in say 10 seconds. So that's typically not possible. Batteries need some time for the chemical reaction in there to happen. Flywheel can be charged in very, very short times, and also be discharged in very, very short times, in the order of like seconds to minutes. And another good thing, the capacity of the flywheel doesn't degrade. So I just got a relatively new phone. That phone gets me now through the day with one charge. My older phone, I had to charge at least twice a day. Otherwise, after a couple of years, the battery degrades and it doesn't have the same storage capacity anymore. Flywheels don't have that. And they're made from very common engineering materials, so they're not really hazardous in any kind of shape or form. However, every energy storage system is hazardous in the sense that it stores a lot of energy. So an energy is if released in an unsafe manner, can be harmful. Like a battery, and if you ever seen a Tesla car have an electrical fault and going up in flames, this is not a fire I want to fight. Or if this happens with a battery system that you have in your basement, it's hard to extinguish a battery fire when you have a large battery. A flywheel mechanical system, there's a lot of rotating parts in there. If that fails, it's a problem, right? So you don't want to have a flywheel failing on you. You can even make the argument for pumped hydro. If a hydro dam breaks and the water is released in an uncontrolled manner, it's a lot of flooding. So flywheels are typically provided these days in systems like the picture here, this cartoon on the right, which is the company in the States that provides these. So in different units. So they're almost like batteries, but each of these is one mechanical system. And I will show you in a moment what they look like. But before I get there, let me show you a little bit where flywheels actually fit into the bigger picture between other storage technologies. So we have here the power that they can provide, and then the typical storage range for these systems. So pumped hydro, very large facilities that can store electricity or energy for long periods of time, and typically for large power supplies. Thermal and pneumatic storage, they all kind of fall into the same kind of area. Flywheels are down here, so they're really good in storing electricity for shorter periods of time. Quite sizable storage system can be created, but they're not really good for storing electricity for days or weeks or even hours, right? So just barely, new technology maybe get into hours, but overall it's not very common. So how does a flywheel work? Well, many of you have probably played with a flywheel system before. This is this kind of Z car here. I like this little thing. So you wind this car up on a surface, and this blue thing, the big flywheel, starts spinning, and you store essentially the energy in this flywheel, and you put it back on the ground, and it kind of pulls the car forward and makes it drive. I like this particular one. I actually had one of those. The Dinky Toys Pink Panther car. Again, here you had a ratchet that you put in there, and you spun up the flywheel very fast. And then the mechanical energy that I put in with my arm to spin up the flywheel was then used to drive this little car around the carpet. So again, that's kind of the idea, right? So you want to put energy in to get something rotating. So here's a picture of an actual energy storage flywheel. And that was developed by a company in Germany, and it's used for energy storage for regenerative braking in train systems. So like LRT or light rail transit systems, that's what this thing is used for. So whenever a train comes into the station and has to brake and electricity is generated during the braking process, this flywheel will store it for a few minutes until the train leaves the station again, and then the process is reversed. So how does the flywheel work? There's rotating parts. They kind of identified with little these little asterisks here. So we have a large rotor, a large mass that's being rotating. And I should say the mass, the faster the thing rotates, the better it is. It's not necessarily the mass that's the most important thing. If you have looked into this before, you probably know that rotating like energy in a rotating mass, the mass only goes in there linearly, but the speed actually goes quadratically. So the faster, the better. So you need strong materials, because you think the faster something rotates, the more stresses, the more forces are being involved. So you need a strong material that can rotate very fast. So the rotor is typically made out of fiber reinforced plastics, like something like carbon fiber, something that is high strength and can sustain the high loads that are being created by these very high speeds that these flywheels rotate in. They're sitting on a shaft, and then we have another rotor down here, which is the rotor of the electrical machine, which is like a motor and a generator at the same time. So this electrical machine down here can work as a motor or as a generator. So electricity is supplied, it speeds up the flywheel. If electricity is needed, this system actually slows down the flywheel and generates electricity. And there's bearings to the thing that has to rotate on something, and there's a housing that keeps all of this in place. Most flywheels rotate at very, very high speeds. So we're talking of tens of thousands of revolutions per minute. Some of them go up to 100,000 RPM. Because the speeds are so high, they would create a lot of friction with air. So the flywheel actually often gets so hot that the material will actually start catching fire. So they typically rotate in a vacuum, also to reduce friction with the air. So the flywheels are, the whole system here is evacuated. There's no air in there. So that's kind of what a flywheel looks like. Here's an actual flywheel, again from this American company. So it's a large cylinder made of carbon fiber. And it's kind of put into this vacuum enclosure here. And then the motor is actually kind of hidden inside in this big, big rotor that we see in the top left of the picture. And then they put these various of those units into these containers, and there's a whole bunch of power electronics involved. And they use this facility, for example, it's Sense in Pennsylvania, has 200 flywheels in these different containers and provides 20 megawatt power for grid frequency regulation. So that's just for a very short periods of time when the electricity demand on the grid rises too fast and the frequency of the grid gets out of whack, then these flywheels kick in to provide electricity for a few seconds or in the order of minutes to stabilize the grid until other supplies like a diesel generator or some gas-fired power plant can come online and take over this extra load. So it prevents like blackouts, brownouts, those kind of things. It's a very clever kind of system. So those are things that I built in the States. The flywheel that we have been working on, that's a smaller version. That's what our test flywheel looks like. That's my grad students have been working on this. I'm going to show you a little bit what this what we have been doing in our lab. So we're actually building flywheels from scratch. So this is everything you see here is done entirely by my grad students. So this flywheel will show in a moment what it all entails. So this is the actual picture of the flywheel. And let's see if I switch to the next slide. Here we actually have a picture of a cartoon, which kind of a cutaway view of the flywheel. Similar to the flywheel I showed you a second ago that was built by this German company. It has very similar components. We have the rotor, which is a carbon fiber rim. And we also combine it with a different material. That's a long story why we kind of combine different composite materials here. They're all fiber reinforced plastics, very high strength. I mean, in Alberta, I always feel like the fiber reinforced plastics, people probably know best from their hockey stick. I mean, a lot of people always seem to react to that as like, oh yeah, carbon fiber hockey stick. Yeah, but other things are made from carbon fibers too that are high performance, like if you have a high-end bicycle, a good tennis racket, things like that, right? Sporting goods often. In high-performance cars, you find compounds like, race cars and so on. So high-performance materials, very strong, to build this rotor. So we have the facilities here to build these rotors. And that's where my engineering design interests come into place, of how to best create these kinds of structures. Then the flywheel has a little hub that's simply made from aluminum. It has bearings that the flywheel rides on. The blue thing is like kind of the vacuum enclosure. It has a burst ring. So in case something goes wrong, that no parts come flying, because we are again building prototypes. So we're trying to be, doing everything right, but you never know, right? So that's why we want to be safe. The whole fly will actually be operating when we test it in a concrete pit in the ground. So nobody can get hurt if anything goes wrong. The flywheel, if you want to get the size, like it's about half a meter in diameter kind of thing. And it's the electrical machine, so the motor generator unit. We keep the electrical machine on the outside. So inside the housing, it's vacuum. Outside, we keep the electrical machine. The reason is we want to decouple this electrical machine. I'll tell you in a moment why. So that's our electrical machine, and it's just simply connected by a magnetic coupling that kind of ensures that there's still a vacuum seal here. So what do we do with this particular system that we designed? So graduate students have been working on it and getting their master's and PhD degrees on various topics. And then, we always develop some theories why things should behave in a certain way, and we can test them using this particular setup. So we have looked at different levels of vacuum. So we don't need like a vacuum like we have it in space, like a perfect vacuum where there's no air at all, which is hard to achieve. So, but what vacuum level, how much air pressure can we tolerate in the flywheel to get the best performance at a certain cost and effort kind of thing? So that's one of the questions. The various bearings, we have looked at like simple steel bearings, like steel roller bearings you find in any bicycle or so, all the way to ceramic bearings, which are much more expensive, but operate at much lower friction losses, to magnetic bearings, so which are the most expensive version of it. So we have tried different bearing systems and characterized the losses in that. We looked at the design of the electrical machine and how the electrical machine affects the system, the materials, and then overall, that's what manufacturing method and assembly methods are most effective to create cost-efficient flywheels. Because I have to admit, flywheels at this particular point, the flywheels I told you for the system in Pennsylvania, they are unfortunately still a little bit too expensive. So costs need to come down on those. Ongoing research that is still going on. I have a couple of things. We want to try, I told you the electrical machine, so the motor generator is a different system compared to the rotor. If you could combine the rotor and the electrical machine into one system, then it would be saving materials and therefore cost. So we're trying to create innovative, additive manufacturing, so 3D printing methods, to try to create this rotor that is actually has a magnetic properties. So we don't need an extra electrical machine. So the rotor, the rotating mass is actually part of the electrical machine, or the electrical machine is part of the rotating mass. Long-term behavior, so flywheels are supposed, because again, they don't degrade the quality, the energy storage capacity doesn't degrade over time with charge-discharge cycles. People say they last 20 years. Question is, who proves that, right? So doing a test for 20 years is kind of cumbersome. So we're trying to figure out accelerated testing methods and also methods to predict the long-term behavior over decades for those flywheels of how they would perform many years from now, and if they're still have the same strength, some of the same performance after so and so many years. And it's not trivial because again, it's a fiber reinforced polymer materials, and they do actually deform slightly over time, especially when they're loaded at these high loads with the high rotation speeds. And the last topic, which is maybe one of the most interesting ones in this context, is how can flywheels be integrated into storage systems. I told you they're only good for a few minutes, like of storing electricity. So they're not the answer to like all our energy storage needs, but they may make systems better. This is actually a cartoon that's from the University of Sheffield, but they're working with a company in Ireland, and they're providing electrochemical batteries, so lithium-ion battery systems with flywheels. And so they're providing when there's electricity coming from the grid, so like from solar or so, they're storing the electricity in the batteries and the flywheels. And when electricity, the flywheels are here to really even out the energy demand and supply. So these battery systems get slowly charged and slowly discharged, whereas the flywheels take care of all the peaks and valleys, all the things that batteries don't like, and batteries degrade much faster. So again, batteries degrade much quicker if they get fast charged and fast discharged. So long-term charging and long-term discharging is the greatest thing for the chemical batteries. Combined with the flywheel, we might prolong the longevity of these chemical batteries and become more efficient as a system to support, say, small communities, microgrids. We got interest from we've been talking to companies around here in Alberta and Canada that are trying to build energy efficient communities. So they would have these microgrid systems that are based on a battery and flywheel system possible. That's one of the things we're working on. Interesting topic. I mean, that's a slide. I think I have Colleen. I'm looking at my team here. That's my last slide. I just want to drop this in here. One project we did last summer was we worked with the city of Edmonton. Some of you may know that the city of Edmonton is, or at least has been looking into converting their diesel bus fleet into electric bus fleet. There's been a big project within the city. I don't know where that project is right now with everything that is going on politically, as well as with COVID and financial situations that the province and the city is in. I'm not sure where this project is going, but it was announced that the always mind-boggling amount of 800 buses within our city will be converted to electric in a few years. And that means 150 buses per bus depot need to be charged. The way buses are operated is they come into the bus depot typically once during midday and then at the end of the day. And when they all come back within a very narrow time window in the midday period, they all need to be recharged. And the electricity grid of the city is actually not built for that, to provide so much energy in such a short period of time. So bus depots will have local energy storage on site to buffer electricity, like have storage capacity to just charge these buses so that they can get back on the road. And what it was easy with diesel, like refueling a bus with diesel takes a couple minutes, but now recharging a bus, an electrical bus, it takes typically hours. So it becomes a real logistical challenge. So storage is one of the systems that are required for bus depots in the future. And the study that we did in the summer with the city of Edmonton was that flywheel energy systems, those, when I told you from the American company that is selling these, they're actually cost competitive to electrochemical batteries. So good news is there are applications where energy storage flywheels have their merit and fit into the bigger system. So that kind of gets me to the end of my presentation. I hope I'm about right in the timing here. If there's any questions, I put my information in there. At the very bottom is my email. If you want to write this down, if you have any questions later on that you want to get in touch with me and discuss something or have some suggestions, by all means, please do so. And with that, I leave it back to my MC to take over.
Okay, thank you very much, Pierre. So we do have about 10 minutes here for questions, and we've had a number of them come in during the presentation, as well as during registration. So we won't be able to answer them all, but one of the questions that came in ahead of time, and which seems to be on a number of people's minds, Pierre, the question is, which large-scale energy storage alternatives are considered suitable for Alberta?
Yeah, and that's when I saw that question in the list, that is a really interesting one. I told you, like in most places on this planet, people would say hydro, pumped hydro is the way to go, but we don't really have the opportunity. There is a solution to that, and it means we have to make much better friends with our friends in British Columbia. If we work closely with them, and our electricity grids would be working better together, we could actually use their storage and expand their storage. But I think in Alberta, we're like very limited what we can do in terms of energy storage. Battery systems will have their place. those systems that I showed you, which are batteries and flywheels, may have their place, especially in smaller communities and microgrids. The Blatchford system here in the city of Edmonton might have some storage capacity, but otherwise in large-scale storage, not sure. There are discussions about those pneumatic storage systems where we might be able to store gas, like air, like a compressed gas, like air underground. But I'm not sure, I haven't heard of any serious proposal where a system like this would be developed in Alberta. So in terms of energy storage, we are at the very, we're not blessed with energy storage capacity within Alberta.
So related to that question, Kristen has asked the question, can water towers be used for pumped hydro?
Unfortunately not. It's because the amount of energy that needs to be stored, the energy density of pumped hydro is not very high. So you either need very, very high towers or you need a lot of towers. And I don't think that is something that is feasible. So for example, for your house, you could not store enough electricity for your house by pumping water into your attic. That's just not going to work. So it would be an excessive amount of structures that would have to be built. And that kind of points to the problem with pumped hydro. You need a lot of land in mountainous areas to fill that. So it's a problem. And so water towers are not really the answer.
Okay, I'm just looking, there was another question here. Somebody had asked about stacking the flywheels, if you are able to reduce the land use by stacking flywheels rather than laying them out in linear fashion.
Okay, yeah, that's an interesting one. I think they do this because where they have these systems, there's just a lot of space. The flywheels that are being used, I know ironically, my hometown in Germany, Hanover, they use these flywheels I mentioned to you for the light rail transit system. They are completely out of sight. They are underground or integrated in existing structures. So for example, flywheels, you don't have to, as soon as they're installed, you can just more or less forget about them. So they would be, you can have them under parking lots, even under roads, right? So if they're designed right, there's very little maintenance that you have to do to those. So you could stack them, yes. You can have them, going into the ground in kind of basement structures. But the simplest solution is simply having having them sitting somewhere under some kind of surface that look, for example, like a similar idea like with the gas station. Like your gas station has all the gas tanks for all the gasoline and whatever diesel fuel and everything stored underground underneath the gas station. So it's out of sight, out of mind. You barely have to get to that like once every decade or so to do something. So same idea with the flywheels. You would just put them out of sight.
Okay, thank you. Robert has asked a question about about the city bus project. Mm-hmm. Could they not use a removable battery pack and keep the charging rates constant by switching out battery packs?
Interesting question. I asked the same question. I'm not even sure if there is a bus system that does that. The issue with the bus system, what I learned, it's highly complex. So the first thing is the best would be to have buses operating at a different schedule so that they have much more charging time in between. The problem is that you have to go from a diesel bus fleet to an electrical bus fleet, and you can't just shut down your bus system for like a month or two and say there's no buses, we're switching over. So the electrical buses would be phased in parallel to the diesel buses, and they have to operate the same way a diesel bus does. So that was one of the issues. And then also the procurement process for those buses is quite complex. So the company that actually provides these buses is actually, I think, now I'm going a little bit on a limb here, but they're also investing in this project. So I'm not sure if this is the ideal bus that they chose, but it's the ideal bus from a bigger perspective. It's not the ideal bus when you think about the charging of the bus. It's the ideal bus from the whole project performance. Like if you look at the economy, and look at the usage of the buses, storage of the buses. So there's lots of thoughts that go into it. And so when we came in there from a storage point of view, it was pretty clear that, you know, we need storage for the buses. But I agree with you. It's removable batteries seems like a simple thing to do, but that's not how it was designed.
Okay. We've had a couple of questions regarding hydrogen. So one of the questions is, have you done any research comparing hydrogen storage systems compared to the systems that you presented on? And somebody else has asked, what are your thoughts on storing energy by making hydrogen and then using it as a fuel in a traditional combustion plant?
I specifically leave hydrogen out of my presentation. There's a colleague of mine, Dr. Mark Sekanel. He is also a member of the Future Energy Systems. His whole field is hydrogen energy storage. Or energy storage using hydrogen, so fuel cells and storage systems. And he's clearly the expert in that field. I'm happy to connect him to you with him. And that is a potential avenue going forward. I don't work in this field, so I have to admit I probably know as much as most of you do. Yeah, it's feasible. Yeah, it's relatively efficient. In Alberta, we do have like a smaller hydrogen economy, so there is infrastructure is to some level in place to work with hydrogen. It's fairly safe. So there are clear benefits to using hydrogen, and that is one of the areas that should be looked at. Unfortunately, I think hydrogen is one of those niche areas for energy storage. So converting water into, when you have extra electricity, cracking water into hydrogen, and then later on converting the hydrogen back into electricity using, like, for example, a fuel cell, or actually even just burning the hydrogen. Those are possible avenues, but I cannot tell you like how those rank compared to other storage systems. And it's really not, as much as I know, nowhere a large scale player on this planet.
Okay. And then I think we have time for one more question here. I'm going to, again, combine a couple of things that have come in. One of the questions isn't the Brazeau Dam an opportunity for storage? And on a similar vein, how come we don't use depleted formation caverns and suspended gas well for storage? We have a lot of that here in Alberta.
Couple of thoughts on that. So let me go to the gas wells and caverns first. The problem, I think, with that is that they're pretty dispersed over the large area in Alberta. Coming from Germany, I'm always amazed how large Alberta is. Like, I mean, I think Albertans have, like, often don't really appreciate that in this province, we're only 4 million people on an area that's twice as large as Germany. So Germany is like 83 million, and it's only half the size of Alberta, and we're only 4 million on a very large space. So connecting to all of these, and the gas wells are all over the place. If you go up north here from Edmonton to the Boreal Forest, there are like wells and, you know, drill sites everywhere. Yeah, there might be opportunities, but the infrastructure that you need to cover these vast distances is expensive. So I think that's probably one of the reasons. And another thing I kind of learned is, I mean, I'm part of another group that is a network of researchers between Bavaria and Germany, and researchers here in Alberta from Lethbridge, Calgary, and Edmonton. And we're looking at the interdisciplinary kind of impact of energy infrastructure or energy use. So, and when it comes to dams and comes to storage facilities, hydro facilities in Alberta, there is a lot of competing objectives. So I learned this last summer. I was at a workshop for a week in Kananaskis country and looked at the hydro facilities there. And like people, I had no idea of what the demands are on these hydro facilities in the Kananaskis Valley. You know, like the Great Barrier Lake and those kinds of things there. So they're supposed to do flood prevention for the city of Calgary. They're supposed to provide high and low tide flow, low and high flow for recreational facilities so that people can do kayaking and do tourism on the Kananaskis River. I mean, if you've ever been at the Widowmaker waterfalls, during the times that the hydro dam is not operating, you can wade through the water. It's like ankle deep. But if you come back a couple hours later, you drown in that thing, right? So it's quite stunning of the demands that are on these particular systems. And I'm not sure, like, you know, just using them from a purely energy storage and energy generation or power generation perspective, they might work, but there might be many other competing objectives that make it impossible to use them for power generation, or at least effectively use them for power generation. So it's not this trivial as a lot of different players that have demands for the very limited hydropower capacity that we have in Alberta. And I think overall it's not going to be a major player, unfortunately.
Okay, well, thank you very much. I think that is unfortunately all the time that we have. I know Pierre actually has to run to the lab, so we want to make sure that he gets back there and maybe even has some time to eat something. So I do want to thank you so much, Pierre, for sharing your expertise with us on this issue. And judging by the questions that came in, there is a lot of information to consider and to go through. So thank you so much for paring it down into a little bit of a tiny bite for us. There's been some suggestions too for more webinars like this, maybe more in depth for those engineers in the group. So we'll definitely consider that going forward. So thank you again, Pierre, for sharing your expertise and joining us today. We do encourage all of you to stay connected with the University of Alberta. There are many opportunities to get involved and stay connected with us virtually. Visit our website and click the on-demand section to view any of our digital content, again, upcoming webinars or previous ones that we've had. All digital content is released on our social media channels as soon as it's available, so be sure to follow us, UAlberta Alumni, on Facebook and Instagram. This concludes our webinar today. We want to thank you very much for joining us and for supporting the University of Alberta. We'll be sending out a survey shortly. So again, if you do have suggestions for future webinars, specifics, please do include that and we'll take it into consideration. Thank you again and good afternoon.
Thank you so much for watching Future Energy Systems video. Make sure to subscribe so you don't miss any of our exciting content. Check out the links below to our website and learning page where you can find activities, learning extension, and more. You can also sign up on the website for notifications for future videos and interactive opportunities. There's so much to learn as we explore our energy future.